All right. Similar problem. Okay. I'm going to go ahead and look at the limit as x approaches 3 from the right. And I'll go ahead and it doesn't matter where I put this. I'm going to move the negative sign up there. It'll just be a little bit easier to talk about as we do this problem. Okay. Negative 2x over x minus 3 quantity squared. Okay. So, folks, this one up here, 8a, is the stereotypical, the quintessential example. Okay? I feel like you can learn it all from this one idea, so now I'm just taking the idea and extending it. All the rest of these are extensions. They're a little bit harder than this first one. Okay? In this case, what's my numerator approaching? Negative 6. So if the numerator is negative, you just invert these properties that we talked about. Okay? So the numerator is approaching negative 6. The denominator is approaching an arbitrarily small what? Positive number. Why? Because I'm plugging in numbers like 3.1, 3.1 minus 3. That's positive. So a fixed negative number divided by something that's arbitrarily small and positive is going to come out to be no hands, no work required, no justification from you, negative infinity. What's the numerator approaching? What's the denominator approaching? Is it negative? When I plug in 2.9 and subtract 3, I get negative. But then what do? Square it, which makes it positive. So we still have a negative over an arbitrarily small positive. So this is still minus infinity. Be careful, folks. Be careful. Okay, you have all the tools you need. You just need to learn to be careful. What I would recommend doing is always returning to the first example. Whenever you get lost with these problems, return to the first example to get your bearings again, and then go tackle the harder ones. Okay. This one, for the transcendental functions, sines and logarithms, and exponentials, you can use your knowledge of their graphs to answer the questions, and that's what I would do. Okay. What does the graph of the natural log of x look like? I hope you remember. If not, there's a video. Okay? So I'm not going to explain it. There's the graph of the natural log function. Of course, it passes through the order pair 1, 0. Why? Ooh, better watch the video. Okay? Let's look at the limit as x approaches 0 of the natural log of x. Right? That's the boundary. What's the domain of the natural log function? Its domain goes from 0 to infinity. So what's the boundary of its domain? 0. Let's explore it. Wait a minute. What's the boundary? 0. Can I approach 0 from either direction? No, because I can only take domain values from where? From the right. It only makes sense to do domain values from the right. Does that make sense? Yeah. Yeah, so the domain is only for positive numbers, and for limits, we can only plug in values in the domain that are getting close to the value that we're taking the limit at. So I can't plug in numbers like, I can plug in numbers like 0.5 or 0.12 or 0.003, but I can't plug in numbers like negative 0.5 to explore how the function's behaving near 0, not because of a limit issue, but because it's not even in the domain to begin with.
Oh, never mind. Oh, I see.
That's all right. That's right. Yeah, I appreciate the questions. Okay. All right. This I said you can just do from the graph. What's the answer? Negative infinity. You never have to, for these problems, you never have to justify to me why the answer is infinity or negative infinity. Okay? Because there's only one way to justify it, and it's a rigorous proof. And we will do that once in 2.7 and say, that's for other folks to do. Let's look at this one. Okay. So I want to look at the limit. Where's the potential vertical asymptote at?
3.
Potentially at 3. So let's approach 3. But what's the issue, folks? Can I approach 3 recklessly? No. Can I plug in numbers like 3.1 for x? Can I plug in numbers like 3.5 for x? No, what's the domain of K? The domain of K, we had domain quiz. This problem was almost on it, almost identical. What's the domain of K? Minus infinity to 3. What goes on the end there? It's a parentheses. So can I just approach 3 from any direction? No, I've got to approach it from which way? From the left. Tough stuff. This is not easy. This is not easy. This is tough stuff. Okay? I'm just going to run through the same analysis as before. Okay? We've got 1 over, so we've got a fixed positive. When I plug in numbers like 2.9, I've got a small positive number. When I take the square root of a small positive number, it actually gets a little bigger, but it's still small and still positive. So we've got 1 over an arbitrarily small but positive number, so we are approaching positive infinity. Okay? No justification required there. Okay, I'm getting the hang of this. Wherever the function's undefined, I've got a vertical asymptote. Is that always true? No, because of the inflection in his voice, it can't be. Right? That's correct. Okay, let's look at this one. Does this have any vertical asymptotes? I don't know. What should we do? Well, we should go look at the behavior near 1. I'm going to go ahead and keep the limit proper until I feel like maybe I'll have to break it down, but I don't think I will in this case. Somebody said, hey, this sounds a little familiar. Let's factor the numerator. We get down to a place where we can do apply the direct substitution. What did this limit not come out to be? Didn't come out to be plus or minus infinity. Do we have a vertical asymptote at x equals 1? No. The limit proper didn't come out to be infinity. The limit proper came out to be 2. So what are the left and right hand limits? They're also 2, right? If the limit proper is something, then the left and right hand limits have to agree, correct? So they're also 2, so they're not infinity either. So there are no vertical asymptotes. In fact, what do we have at x equals 1? At x equals 1, f has a hole. Okay. If f is undefined, I should have put at x equals a, but the limit as we approach a exists, then the graph of f has a hole at x equals a and not a vertical asymptote. That's the best generalization I can give you. Anything else would be a lie at some point. Okay? So if the function's not defined there, but the limit proper exists, then you've got a hole there. Okay? Warning, if the limit does not exist, that does not necessarily mean that f has a vertical asymptote there. We've seen lots of examples of that. So for example, we had this one last time, the graph of this function. This was the graph of f of x equaling the absolute value of x minus 3 over x minus 3. Does the limit exist at 3? No. How come? The left and right hand limits don't agree with each other. Do I have a vertical asymptote at 3? No. So anyway, in fact, I have holes there, but they're kind of left hole and right hole.